Hello everyone, and welcome to Moxa's webinar, Cybersecurity Best Practices for the Industrial IoT. I'm Martin McHugh, and I'll be your moderator today. If you have any questions at any time during the webinar, please use the questions pane by simply typing in your question and clicking send. At the end of the presentation, we'll do a Q&A session and take as many questions as we have time for. We will follow up with all unanswered questions after the webinar. Today's presentation will be around 30 minutes with an additional 10 to 15 minutes of Q&A. Okay, let's get started. Today's presenter is Richard Wood. Rich is the Product Marketing Manager of Industrial Ethernet Infrastructure for Moxa Americas. For over 2 decades, Rich has worked in the trenches with plant engineers and OEMs to increase manufacturing efficiency through industrial automation solutions. He has contributed to successful implementations in automotive, semiconductor, textiles, packaging, and other industries. And with that, I'll hand it over to Rich.
Thank you, Marty. All right, so here's today's agenda. We'll begin by reviewing the cybersecurity landscape in today's Internet of Things era. Then we'll jump into some unique challenges for industrial automation. From there, we'll begin to discuss some of the standards that have emerged around industrial cybersecurity and get into some best practices. And then finally, we'll wrap up with a few case studies and get into the Q&A. The IoT, or Internet of Things, refers to devices, systems, and services communicating with each other via the Internet to enable smarter operations and new applications. The IoT spurred terms such as intelligent cities, intelligent highways, and smart factories. But what does that all really mean? Let's look at an example that many of you may relate to. For years now, many Department of Transportation agencies have been using traffic cameras and ground sensors to monitor traffic and road conditions on our major highways. These systems were typically private networks accessible only to agency personnel at regional control centers. Through the Internet of Things, many of these sensors, cameras, and the data they create are accessible via the Internet. The accessibility of this data has spurred the development of applications and services to provide better information to municipalities and drivers alike. In the past, the video and road sensors on a highway could allow someone in a control center to detect an accident and dispatch emergency services. Now, those same video cameras, sensors, and other data can be shared securely over the Internet to allow local municipalities to more efficiently reroute traffic on surface streets near the accident, and even alert drivers through their vehicle navigation systems or cell phones that there's an accident ahead and calculate a route around the trouble. Industrial engineers are becoming more aware of the importance of network security in today's industrial systems. Attacks on industrial control systems are becoming more commonplace. The availability of industry-specific search engines, which can reveal systems to anyone interested, has made it easier to target vulnerable systems. Years ago, networks that were not connected to the public network were considered safe. Today, these networks are interconnected, and the challenge is how to make them secure. This has caused industrial engineers to go back and secure existing systems, as well as rethink their network deployment strategy. This webinar will address some of these topics, as well as provide best practices in securing industrial networks. Cybersecurity has long been a concern at the enterprise level, but we've seen a dramatic increase in the number and frequency of attacks on critical infrastructure and manufacturing. These attacks come not only from malicious external hackers, but also from internal sources. As I talk to executives, managers, and engineers about industrial cybersecurity, one of the statements I continue to hear is that none of our SCADA or ICS equipment is accessible from the Internet. Many of these same people are surprised to find out that they're more vulnerable than they thought. Project Shine was developed to extract information about the existence of SCADA and ICS devices accessible from the Internet. The project used an existing online search engine called Shodan that scans the Internet looking for attached devices. Those devices can be computers, printers, switches, PLCs, SCADA RTUs, or anything with an IP address. To date, Project Shine has uncovered over 1 million connected SCADA and ICS devices, and continues to find new ones at a rate of roughly 2,000 to 8,000 a day. The point is that there are more devices connected to the internet than most people believe, and if a simple search engine can see them, so can the bad guys. In response to the growing number of attacks on critical infrastructure and the prevalence of tools like Shodan, the U.S. government felt the need to weigh in on the subject. On February 12, 2013, President Obama signed Executive Order 13636 for improving critical infrastructure cybersecurity. The executive order is designed to increase the level of core capabilities for our critical infrastructure to manage cyber risk. It does this by focusing on three key areas: information sharing, privacy, and the adoption of cybersecurity best practices. To address the information sharing, the Department of Homeland Security has formed ICS CERT, or the Industrial Control Systems Cyber Emergency Response Team. ICS CERT collaborates with international and private sector computer emergency response teams to share control systems related security incidents and mitigation measures. ICS CERT Alert is intended to provide timely notification to critical infrastructure owners and operators concerning threats or activity with the potential to impact critical infrastructure computing networks. To help in the adoption of cybersecurity best practices, the National Institute of Standards and Technology released their Guide to Industrial Control Systems Security in 2014. This document provides guidance for establishing secure industrial control systems. These industrial control systems, which include supervisory control and data acquisition systems, or SCADA systems, distributed control systems, and other control systems such as PLCs. Here's today's first poll. What are your biggest industrial cybersecurity concerns? Is it protecting critical devices from external threats? Protecting critical devices from internal threats? Providing secure remote access? Or isolating critical devices from other network traffic? If you could just go in and choose the one that's nearest and dearest to your heart. We're all curious to see what kind of trends we get here. Okay, we've got a couple more seconds here. Looks like we're getting close to everyone having voted. All right, so let's share the results here. It looks like almost half of you are concerned with providing secure remote access, followed by protecting critical devices from external threats. And then we've got some interest in isolating critical devices from other network traffic, and not a lot of concern about protecting critical devices from internal threats. Okay, well that's really good feedback. Okay, so now let's talk about some unique challenges for industrial control systems. Initially, ICS had little resemblance to traditional information technology systems, in that ICS were isolated systems running proprietary control protocols using specialized hardware and software. As these industrial networks converge and become connected to enterprise-level systems and the internet at large, there are some unique challenges in providing security while maintaining critical functionality. It's important to realize that the types of threats and consequences of a breach can be very different than in traditional enterprise-level security breaches. Simply delaying a flow of information in an industrial control system could disrupt the operation of an entire production process or line. Unauthorized changes to instructions, device configurations, or operator information could result in damaged, disabled, or shut down equipment. In addition to the cost to repair, lost profits, and typical costs associated with a breach, there can also be environmental impacts and even endangerment of human life. Additionally, the equipment used in industrial control systems has to be able to operate reliably in harsh industrial environments. Enterprise equipment is typically designed to operate in air-conditioned server rooms where the environment is closely controlled to optimize the function and reliability of the IT equipment. Industrial equipment is often found out on the factory floor, where it's subject to extreme temperatures, shock and vibration, electromagnetic noise, and even pollution. Furthermore, many of these industrial protocols were never designed with the idea that they would be connected to the outside world. and so they don't have robust security built into the protocols themselves. While enterprise-level security devices typically filter packets based on IP address or port, industrial devices need to be able to look deeper into the packets of data to the commands embedded in the application layer in order to filter potentially harmful data. They also need to be able to do this without introducing delays in transmission that could cause a malfunction. In the example here, an HMI has access to a Modbus TPC device for monitoring purposes. The intent is for the HMI to have read-only access to the device. Since the read-write function codes are embedded in the application layer of the Modbus TPC packet, a traditional firewall will see that the HMI has been granted access to the device, but cannot tell if the packet is asking to read or write data. The write command could cause a potential system failure. With deep packet inspection, information at the application layer is inspected to allow only read access to the device. Any packets attempting to write are discarded. Just like in enterprise systems, firewalls are an important tool in industrial cybersecurity. Here's a side-by-side comparison of an industrial grade versus enterprise grade firewall. You can see that both devices are designed to protect very different types of devices. They're designed to operate in different environments, and they're designed to filter different types of content. It's important to note that an enterprise firewall is likely not going to provide adequate protection for an ICS. From a practical standpoint, when looking at security for industrial networks, there are two main concerns. The first, which most of you were concerned about, is secure remote access to systems. As plant networks become more dispersed, it becomes necessary to provide for remote control and monitoring of critical systems while protecting them from unauthorized access. Industrial secure routers use encrypted VPN tunnels to provide easy, secure access at a reasonable cost. The second is critical device protection. In a production environment, not only do you need to protect critical devices from unauthorized access, but you also need to protect the network from other devices on the network. For example, a malfunctioning PLC, if not properly isolated, could easily broadcast enough traffic to bring down the entire network. Industrial firewalls can provide the proper protection and isolation necessary. These firewalls are specifically designed to filter the types of traffic harmful to industrial networks. They're also designed to be installed without having to reconfigure the rest of your network. In our discussions with control engineers, a question that comes up a lot is what standards exist to govern cybersecurity for industrial control systems. Depending on what industry you're in, there's a handful to choose from. If you're in the oil and gas industry and you're securing pipeline systems, you should note that the TSA actually governs pipeline security guidelines, since technically a pipeline is a method of transport. Detailed information about those guidelines can be found at the TSA website. If you're in the power industry, the North American Electric Reliability Corporation standards, or NERC-CIP D5, will be the one you'll want to look at. For most of us, though, ISA or IES 62443 will be the standard we look to for securing industrial control systems. I'll go into this standard a little deeper in the coming slides. So what is ISE IEC 62443? The ISA worked on defining security standards for several years, resulting in ISA 99. The first of these parts were approved by ANSI later that year. In 2010, the standards were renumbered to be ANSI ISA 62443 series. This change was intended to align the ISA and ANSI document numbering with the corresponding IEC standards. ISA IEC 62443 is a series of standards, technical reports, and related information that defines procedures for implementing electronically secure industrial automation and control systems. This is an overview of the 14 components of the standard. While this is rather complex with a lot of moving parts, processes, and policies, I've tried to boil it down to some practical first steps. Keep in mind that security is an ongoing process, or a lifestyle, if you will. The following slides will outline some initial areas to look at to do an initial assessment of your risks. And that brings us to our second poll question. How would you describe your current industrial cybersecurity practices? Are none of your devices connected to the enterprise network or internet? Are you just starting to investigate industrial cybersecurity? Are you implementing changes after an initial security audit? Or do you currently maintain a continuous improvement process around cybersecurity? Please take a couple of seconds to just choose the answer that most fits your situation. We're really interested to see where people are in kind of the life cycle of cybersecurity in their industrial control systems. All right. So it looks like 52% of you are just starting to investigate industrial cybersecurity. Then 33% of you maintain a continuous improvement process, with roughly 7 to 8% of you either not connected to your enterprise network or implementing changes after an initial security audit. So now that we've had a little understanding of some of the risks, the unique challenges, and standards around securing industrial control systems, let's look at some best practices. Best practices, they often refer to a defense in depth strategy. From an industrial standpoint, I've broken this down into two main principles. The first is to defend multiple fronts or access points. Start by looking at the existing data lines into the network and set up defenses to keep unwanted traffic from flowing through those connections. Also look at physical access point at edge devices. Are there unused network ports that someone could plug into and access your network? The second principle is a layered defense. The more checkpoints someone has to go through to access critical infrastructure, the more opportunities you have to detect that intrusion, cut off their access before they get at something important, and set up preventative measures to keep the intrusion from happening again. Think of cybersecurity as an ongoing continuous improvement cycle. To stay secure, you need to be constantly assessing threats, implementing countermeasures, monitoring, and reassessing. At first, you're likely to make some big improvements in your level of security. But as you begin to uncover and fix the vulnerabilities in your network, the improvements will likely become less involved, often consisting of security patches for your various devices. Another successful tactic is segmenting your network into physical or logical zones with similar security requirements, then clearly defining the necessary interaction between those zones and restricting unnecessary traffic and access. Controlling physical access at the edge devices is an often overlooked precaution. An open Ethernet port may look inviting to someone looking for quick access to the internet, but could wind up being devastating to your industrial control network. Utilize centralized user management and authenticate users and devices connecting to the network, and only allow authorized devices to connect. Consider using MAC address control on edge ports and disable any unused ports. And finally, use data encryption to protect data in the event that it's intercepted during transmission. So let's bring some of this together into a simple example. Here we have 3 separate plants in a manufacturing complex. Each have been defined as a separate zone, and the necessary network interactions have been defined between those zones. Industrial firewalls are then used to manage the network traffic between those zones to only the traffic that has been deemed necessary. Furthermore, the conduits between those zones are encrypted using VPN tunnels in the event that someone somehow gets access to the data flowing through those conduits. If we drill down into one of those plants, we can see that it's further broken down into smaller zones with clearly defined points of interaction between them. Multiple levels of firewalls are used to contain network traffic within each zone while allowing defined interaction between zones. All right, one more poll question here. So who is responsible for the security of your industrial networks at your company? Is it your IT department? Or is it your production or plant engineering? Alternatively, Does your IT department lead with help from plant personnel, or does plant personnel lead with help from the IT department? If you could take a few seconds to just choose the situation that most closely reflects your situation. And it looks like we just have a couple more people. All right, so it looks like a little more than a third of you say that your IT department leads this effort, with a tie between IT leading with help from plant personnel and plant personnel leading with the help of the IT department. Only 14% of you say that your production or plant engineering heads up this initiative. So in a typical layered approach, it's common to see firewalls at the site, zone, and cell level. If you were to look how a typical firewalls require you to set up different subnets on either side of each firewall, you could easily find yourself with a very complex network that needed a lot of configuration. Luckily, another feature of industrial firewalls is the transparent firewall or bridge mode feature. This allows you to put a firewall between any two devices, zones, or sites without having to reconfigure subnets. This can make your overall network much simpler and easier to manage. As we mentioned earlier, detection is a critical part of a defense in depth strategy. It is the beginning point for your cybersecurity continuous improvement process. Many enterprise IT professionals rely on security information and event management software to collect and analyze detected attempts to breach their systems. In an industrial control system, this data can be fed directly into those enterprise SEIM systems, but also has the capability for real-time intrusion detection and alerts so that action can be taken to protect critical infrastructure before an intrusion is successful. Finally, a firewall is only effective if it can filter out the harmful traffic. In industrial control systems, firewalls must be able to look deeper into the application layer data within the packets in order to effectively protect your systems. This deep packet inspection allows you to set up firewall rules at the application level to ensure that you're catching all of the potentially harmful traffic. So we've talked about some theory and some general application. Now let's wrap things up with a couple of real-life examples to bring these concepts together. In this case, a semiconductor manufacturer had well over 1,000 laser equipment stations that required real-time communication within the station itself, as well as relying on communication with multiple wide area networks. It was critical that broadcast traffic from the other stations didn't interfere. Industrial firewalls were used to allow these secure connections to wide area networks while isolating the broadcast traffic within each station. With so many firewalls in use, simple configuration was also a key feature. Overall, they were able to provide a reliable and stable network for their mission-critical application. In this gas pipeline application, hundreds of stations were strung out over thousands of miles, yet needed to be connected back to a centralized control center as well as to each other. Due to the distances involved, dedicated network connections were not an option, so public networks needed to be used to connect the individual stations back to the control center and to each other. Modbus TPC industrial protocol was in use at the stations. Industrial secure routers were used to provide firewall protection with deep packet inspection, as well as secure VPN connections to encrypt data going over public network connections. Hopefully I was able to give you a basic understanding of some industrial cybersecurity principles and best practices today. I'll remind you, if you have any questions, please feel free to type them in the Q&A answer, and I'll answer as many of them as possible in the time allotted. So Marty, what questions do we have?
Great, Rich. Thank you so much. Ton of information there. Hopefully everyone found it useful and they can glean what they can from it. But yeah, we have some questions. Let's open it up. The first one I have is from Jason. He asks, I'm pretty experienced with SCADA systems and other industrial controls, but I am not an IT expert. Is setting up a firewall something someone like me can do, or do I need a real IT professional to handle this? So maybe just help Jason out.
Thanks, Jason. Great question. I'd always advise if you have access to an IT professional, definitely get some consultation from them. But I will mention that our industrial secure firewalls are set up with user interfaces that you're likely to find familiar. Additionally, we've built in some setup wizards to guide you through the setup process. And our applications group can certainly help if you get stuck. We can also provide consulting services if you need to help you if you need it.
Great, thanks so much, Rich. The next question I have is from Mark. Mark wants to know if you recommend setting up DMZs as part of your defense in-depth strategy. So maybe share some insights there.
Sure, thanks for the question, Mark. DMZs, or demilitarized zones, are common practice. They're typically set up as a layer of protection between the enterprise network and the industrial control system network. There are industrial secure routers that are set up to help you easily configure this type of layered protection should you decide that that's what you want to do.
Great, thanks again, Rich. The next question, and we have a few more of these, but the next question I have is from Daniel. He asks, our remote sites require redundant WAN connections. With that being the case, how would we configure a firewall to address this?
Thanks, Daniel. Yeah, redundancy is really a core competency of industrial networking equipment in general. There are very few industrial applications that don't require some sort of redundancy in the event that one of the devices fails. Many of the industrial secure routers do have an option for redundant WAN connections, and those will switch automatically between the primary and backup connections in the event of a failure. Best practice would also be to actually install two firewalls, both with redundant WAN connections, and connect both of your incoming WAN connections to both of them, so that if one of the firewalls goes down, you're still up and running.
Great, thank you again, Rich. I have another question from Patrizio. He asks, I hear a lot about stateful firewalls. He wants to know if this is the same as deep packet inspection.
Oh yeah, great question, Patricio. That's a question we get a lot, actually. A stateful firewall keeps track of the state of network connections, such as TCP streams or UDP connections, and is able to hold significant attributes of those connections in memory. These attributes are collectively known as the state of the connection and may include details such as IP addresses and ports involved in the connection, and the sequence numbers of the packets traversing the connection. While our industrial firewalls are stateful, deep packet inspection is considered to be an additional level of inspection above and beyond that, which actually looks at the application layer data in addition to the network layer data. This provides more security, but also it does take a little more processing power to make sure that you get adequate throughput.
Awesome. Thanks again, Rich. We do have a few more questions, so feel free as well for all those left on the broadcast. Submit your questions, and we'll get to them as we can as time allows. The next question is from Francisco. His question, based on your presentation, is it meant that any network is really unsecure if you only relay on the fact that it is not connected to the internet? So if you need further clarification on that question, let me know, and I'll pose that to Francisco so we can respond in. But if you're good, just feel free to answer.
Okay, if I understand your question correctly, a network is not necessarily secure even though it's not connected to the internet. I think that the 2 points I was trying to make was, first, that many more industrial devices and networks have found their way onto the internet than people may believe. The other is, even an industrial network that is not connected to the internet still is at risk if somebody were to come in and, say, plug in their laptop to an open port, thinking that they can get to the internet and somehow set up a loop or potentially download some malware that they didn't know that they had on their laptop. So even though you're not connected to the internet, there are still some risks.
Great. Thank you so much, Rich. Thank you to everyone for your interest and participation. Thanks again for tuning in, and have a great rest of the week, everyone.